Welcome to this podcast from Neurogastroenterology and Motility. It publishes original research and topical reviews on basic and clinical aspects of gastrointestinal sensation and motility, as well as brain-gut interactions.
So welcome everyone to this month's podcast from Neurogastroenterology and Motility. My name's Adam Farm and I'm a gastroenterologist at the Wingate Institute in London. This month it's my great pleasure to welcome Professor John Furness. John's a Professor of Anatomy and Neuroscience at the University of Melbourne and has wide-ranging interests from the effect of nutrients and food components on gut health to the role and pharmacology and indeed therapeutic potential of ghrelin. So John, welcome to this month's podcast and congratulations to you and your co-authors on your paper entitled Site and Mechanism of Colokinetic Action of the Ghrelin Receptor Agonist HMone. So John, what do we know about the effects of ghrelin agonists on gastrointestinal motility and what's their mechanism of action?
Well, the effects on the large bowel are quite clear and have been shown with agonists of different chemistries that act on the ghrelin receptor, and there, in both animal models and in some human studies, it's been shown that there is an increase in defecation, increase in emptying of the colorectum. Other effects have been reported, such as increase in gastric emptying and some anti-ileus effects. It's not really clear how these occur, and they may in fact be indirect effects. For example, ghrelin and ghrelin agonists are strong stimulants of appetite, and we know that when appetite increases, there's a cephalic phase, and you get some increase in activity in the upper GI tract. Trying to use agonists for the large bowel has so far looked successful. Trying to use agonists to increase gastric emptying or to reduce ileus have produced variable results, and in general the pharmaceutical industry has moved away from those attempts.
So we know from Richard McCallum's work that ghrelin has been shown to reduce the frequency and severity of nausea and vomiting, as well as overall gastroparetic symptoms in diabetics. But why hasn't this really been developed further?
Well, I think the first thing to say is that that's now quite recently been confirmed with another drug, relamorelin. This is from Camilleri's group. And so with two compounds of quite different chemistries, a reduction in nausea and vomiting has occurred. So it looks like this is something that will occur independent of the chemistry. Ulimorelin had some disadvantages because it's applied intravenously, which is not a really convenient way to give a drug for conditions that are really not threatening the patient too much. It also has a fairly complicated chemistry. It's a large macrolide. So the reasons might be that it just wasn't the best drug to move forward with, whereas it looks as though the rather simpler compound relamorelin will be used. So I think the target is still a valid one, and I expect that that some of the companies will move forward in this area, but ulimorelin may end up not being the compound of choice.
And I think you've previously demonstrated in your group around it having effects on blood pressure. Is that right?
Yes. Ulimorelin appears to have some off-target effects, although these are at higher doses, and whether that would end up going against use of this drug, I'm not sure. So I think the general idea that compounds acting on ghrelin receptors might be useful in dealing with nausea and vomiting seems valid because two compounds of quite different chemistries have been reported as having the same effect.
So that brings us nicely on to HMone. So could you give me some background to this and what are its differences in its chemistry and indeed mechanism of action?
So HMO1 is a small molecule agonist. Its mechanism of action was not really quite clear, and this is one of the reasons we started looking at it. It turns out that HMO1 is more potent than many of the other compounds that have been tested. That gives hope that it might have greater specificity. Generally, this is a very broad generalization, but generally, the more potent a compound at the target, the more likely you are to have a specificity over off-target effects. The other thing about HMO1, it's readily orally available, so it has advantages over compounds that might be injectables.
Absolutely, I think that's a real attraction of the compound. So, what was your hypothesis as you embarked on your study?
Well, it wasn't so much a hypothesis, it was seeking to understand the mechanism of action, because it had been suggested that the colokinetic actions of HMO1 were due to an action in the hypothalamus or in the brainstem, whereas other compounds, so the agonist receptor, had been shown to act in the lumbosacral area in the defecation centre. So we wanted to see whether it did indeed have its primary action in the hypothalamus or in the brainstem, and also interested in another property of compounds acting at these receptors, in that they tend to desensitize. We didn't know whether a compound with another chemistry might desensitize. In the end, what we did find is that its primary action in colorectal activity is in the lower spinal cord. It might have some actions at other sites, but that's where its primary effect is. It is very potent when given to animals, at least, but unfortunately, it also desensitizes. So the desensitization is probably a property of the receptor and post-receptor mechanisms, and is independent of the chemistry of the agonist. So we're sort of stuck in the way with all of these compounds having a tendency to desensitize with successive application.
So how would you, or rather, what methods did you use to investigate those findings?
Well, we used a method that's been standardized as a screen, and this is to use rats and to measure colorectal propulsive activity in emptying. The reasons we did that is because the other compounds that have gone into clinical testing had been screened in that way, and we knew that, for example, caprimulin, which has been tested, that if it was effective in the rat, it was likely to be effective in the human as well. So it was a very simple way of going ahead with the studies. Obviously, you have to move much further forward into human trials under similar circumstances.
Super. So what do you think were your key findings, just to summarise those again briefly?
Well, quickly, the key findings: it's a potent compound, it's orally active, has good central penetrance, it has major actions on the spinal defecation centres. They're the real key results.
And what do you think in terms of moving this forward now? What do you think are the key next steps in developing this compound, maybe indeed for clinical use?
Well, I think that first of all, if we compare with what's been done with some other compounds, they've been tested in humans in spinal cord injury. In animal studies, the HMO1's been tested in animal models of Parkinson's disease. In both, and in some studies, functional constipation, in which constipation in animals has been induced by low-fibre diet, these compounds have been used and effective. The only human study of constipation has been one done by the Camilleri group and one done in spinal cord injured patients who have a constipation. In both cases, the compounds had some effectiveness, but the studies are small, and the other indication, Parkinson's, has not been tested, although preclinical work has been done with HMO1 in Parkinson's. So I think these classes of compounds have good potential, and I suspect HMO1 is one of the most likely of these to succeed because of its potency, lack of side effects so far discovered. You never know what turns up with this, but so far no side effects. And as I said, it's ready oral availability.
So in the broader sense of the field, where do you think the knowledge gaps lie currently, and how should we go about resolving those in the future?
Okay, I think the major knowledge gaps are we're uncertain of the effectiveness of these types of compounds in humans with repeated dosing, because all the studies that have been done so far have been short-term. And we need to know whether these compounds have longer-term side effects or whether they, with repeated dosing, will lose effectiveness. So we don't know that. Also, we don't know, and we need to know, whether compounds that promote defecation in humans are going to be effective in all types of constipation, and particularly long-term constipation, where the bowel itself might deteriorate and you get a sort of flaccid bowel syndrome. It might be that these compounds fail to act. They may be useful if the constipation is not long-standing. So we don't know that. We need to know, what types of patients might be responsive, what stage of their disorder they might be responsive in, and whether repeated use of these compounds is going to be effective, and whether repeated use might reveal some side effects. So there's quite a lot of unknowns, even though there's good clues that we might be on the right track.
But I think overall within the field, it's a really exciting time with the new secretagogues that we've now got available in the clinic, and indeed new compounds that are being developed. So, John, with that, I'd like to thank you and your other co-authors for a really excellent paper, and indeed for assisting in this month's podcast, and also our listeners for tuning in. And I look forward to welcoming you again on another instalment next month.
Thank you.
Further information about this paper can be found on the journal website. We hope that you have enjoyed this podcast, and we look forward to welcoming you to next month's